tell you 2 moles. And so this is in megapascals. What is megapascals? 10 to the 6 pascals. 10 to the 5 pascals is 1 atmosphere, so 10 atmospheres. So we're measuring this in 10 atmospheres. Okay, so 5 megapascals. They got it backwards. 5 liters. Until the volume is doubled. So this is 10 liters. Then it's cooled isochorically. Isochoric is also a different word for isovolumetric. So this is 10 liters and 1 megapascals. The gas is now compressed isothermally until its volume is back to 5 liters. So but its pressure is 2 megapascals now. 2. Finally, gas is heated isochorically. This is step 4. Step 3. Draw the 4 processes on the PV diagram. There. Find the total work done by the gas. What is the work done by the gas? This is a cyclic process clockwise. The work done is the area under this curve minus the area under this curve, which is just equal to this area. Okay. The work done on these curves under these curves is 0. So we'll have to do this integral and then this integral. Okay. So the work done in process 1 plus work done in process 3. Work done in process 1 is initial volume was 5 liters, final volume was 10 liters. Okay, I have to go to a new page. Okay, they don't give us the temperatures here, but we don't need the temperature because PV equal to nRT. Okay, so you can write this as P1 V1. That's we have the initial volume and pressure here. Okay, and PV remains constant here, and we have P3 V3 here. And in the first process, the final volume is 10 liters, the initial volume is 5 liters. So this ratio is 2 plus P3 V3, this pressure and volume, And the final volume here is 5 liters, initial volume was 10 liters, so that is log of half. And this quantity will be negative. Okay. So P1 is 5 megapascals. Volume is 5 liters. Log 2 plus P3 is 5 liters, 2 megapascals, 5 liters, log a half. So this works out to 5 times 5, 25 to the power 3 log 2 minus 10 to the power 3 I made log half as minus log 2. Okay. So the work done is 10,000 joules. Okay, again, for this process, the work done under this area and under this area. Okay, under 2 isotherms, and that's the formula for the work done under an isotherm.
Oh, where did you pull P1, V1, and P3, V3?
P1, V1 is here. Okay, so the ideal gas law says PV equal to nRT. We didn't have nRT, but this is equal to PV, and it's an isothermal process, so PV is, you can take on any point.
Oh,
So we took it there.
and then P3, V3, you took the 5 liters.
Mhm. Winnie? Go ahead. You won't be able to sleep if you don't say it.
I was just gonna ask you to go back for a second. Okay, that's it.
All right. So again, here's a cyclic process. In the process AB and BC, 3,600 joules and 2,400 joules are added respectively. So here, 3,600 joules. Find the work done in each of the process A, B, BC, and AD, and DC. So the work done here and here are 0. We'll calculate the work done here and here. Find the internal change in processes A, B. So find the internal change. Find the internal energy difference between C and A. Okay. What this problem illustrates is the following. Okay. E is a state function. What does this mean?
It's based on the endpoints.
Based on the state of the system. Each point on this graph represents the state of a system. The internal energy at this point, it doesn't depend on how you got there. It just depends on the state of the system. The internal energy at this point is just depends on the state of that system. So the change in internal energy from here to there doesn't matter how you got there, is a fixed amount. So this problem will illustrate that. We'll calculate the change in internal energy going along this path, going along this path, and they'll come out to be the same. What is path dependent? Work done, and what else? Heat added. Okay, so that was the statement about this first law. This guy is path dependent, this guy is path dependent. Their difference is path independent. Okay, and that's what this problem illustrates. Everybody understand? All right, so for instance, if you go along this path, how much heat did you absorb? 3,600 per, that's 6,000 joules. Okay, and the heat added along this path will be different. The work done along this path is different. The work done along this path is different. Okay. So there's a bunch of calculation, but that's what's going on. Okay. So the work done along AB is what? 0. Everybody understand? Okay, so we calculated the work done along all the 4 segments. Find the internal energy change in the process A, B, and BC. Okay. You going from A to B, you added this much heat and you did 0 work. And then change in internal energy going from B to C. What?
Does that say 2,000 or 3,000?
Which one? This one is 2,000.
Okay.
5 times 4
No,
is,
sorry, I mean on the graph.
this is 3,600. That's 2,400.
Oh, okay. Thank you.
So in going, change in internal energy in going from B to C, the heat added is that much. And the work done B to C is 2,000 joules. Okay, so in going from A to B, your internal energy increased by that much. In going from B to C, your internal energy increased by that much. So,
Why is the work for A and B and the other one 0?
the area under that curve is 0.
Oh, okay.
Find the change in internal energy between C and A. How much did the internal energy? Change in internal energy from A to C is equal to change in internal energy from A to B plus B to C. 3,600 plus 400. 4,000 joules. Find the total heat added in the process ADC. ADC. Okay, this change in internal energy you get to see, no matter how you get there, the change in internal energy is the same, which is 4,000 joules. We don't know this QADC, but we know the work done in that process. AD is 800 joules, 0, 800 plus 0. So the amount of heat added in that process is 4,800 joules. So you see, what we have found is, what we've shown is, well, if you go along this path, you've added 6,000 joules of heat. If you go along this path, you've added 4,800 joules of heat. If you go along this path, you've done 2,000 joules of work. And if you go along this path, you've done 800 joules of work. So you see, heat added and work done are path dependent. From this process, from this information, can you find the heat added in the process AD? Well, we've calculated the heat added here, but we can't do the heat added here because we don't know the heat added here. Okay. So, no, we do not know QAD and QDC. Winnie, what does dilute diatomic gas mean? Dilute means?
That it behaves ideally.
Very beautiful. Okay, so it's an ideal gas and it's a diatomic gas, and if it's probably at room temperature, what that means is the number of degrees of freedom is 5. So 1 mole of a dilute diatomic gas occupying a volume of 10 liters expands against a constant pressure of 2 atmospheres when it's slowly heated. If the temperature of the gas rises by 10 degree Kelvin and 400 joules of heat are added in the process, what is its final volume? So N equal to 1 mole. Pressure is 2 atmospheres. Okay. Okay, so so work done is final volume minus H. We know the work done. Oh no, we don't know the work done. Okay, so if we know the work done, we know the pressure, initial volume, you can calculate that. So we have to find the work done. Okay. Change in internal energy is Q minus W. Okay. Change in, we know the heat added. Okay. So well, we have to find the work done. We don't know this. Change in internal energy is N CV delta T. For a diatomic gas, CV is, so we're assuming this is happening at room temperature. Okay. So the work done is Q is 400 joules minus 1 times 5 halves times 8.314 times 10. So 192 joules of work was done. So we'll substitute that back in there. We'll divide that by P and then add initial volume. Okay. So how much work was done? 192 joules. And at 2 atmospheres. Initial volume was 10 liters. So this is 192 over 20 into 10 minus 3 meter cube plus 10 liters. And this is a liter. So this is 9.6. So the final volume was 20 liters. Yep.
Is it a good rule of thumb to always change liters to
Meter
to
cube.
negative meters cube?
1 liter is 10 to the minus 3 meter cube.
Well, I'm just asking if we should always do that.
So, no, well, in these formulas, if you use everything in SI units, this comes out in meter cube. And so this many meter cube is a liter. This was a liter, so. So in this formula, it's actually two different units. This is meter cube, this is liters. Pressure and volume measurements of a dilute gas, that means it's an ideal gas, undergoing a quasi-static adiabatic expansion. What does an adiabatic expansion mean? No heat exchange. Winnie, 2 for 2. Batting 1,000, girl. So, in an adiabatic process, what is constant? No. PV to the power gamma is constant. So what that means is PI gamma to, or I won't use I. P1 V1 gamma, P2 V2 gamma. You can take any of these 2 points, okay, any point. Take pressure, volume to the power gamma, that should come out to the same value. So for an adiabatic process, this is constant, okay? So let's choose 2 points that are convenient. So we'll choose this point, this is 1, and we'll choose this point, okay? So what we should have is, and since these, we don't have to convert the units because, okay, the multiplication factor will be the same. Okay. So we should really have 20 times 1 to the power gamma should equal 1 times 8.4 to the power gamma. So 20 should equal 8.4 to the power gamma. And so now you can solve for gamma. Okay, so whenever your variable is in the exponent, you take log 20 equal to gamma log 8.4. What does gamma tell you? Gamma is the ratio of specific heats, but what does it tell you?
How complex the
Very good.
gas
Mhm.
molecule is.
Mhm. Mm-hmm. 1.4. So what kind of molecule is it? Diatom. Yeah. Okay. So you see from this table of numbers, you were able to figure out that it's a diatomic gas. Pretty neat. See, you learned a new skill. Almost.
What do you look at to know that that's diatomic? Like, is there a chart that I missed?
Wasn't it the chart from earlier in the PowerPoint?
Here.
Okay.
So gamma is the ratio, and for diatomic gases, gamma was. For monoatomic gases, it's 1.67. Okay.